Hi Year 12. Today's topic is looking at proofs using vectors. And there's not going to be any new content in today's work. It's just using the content that we've already used and basically seeing if we can develop some proofs based on some diagrams for that. So there's a few that I want to go through and there's a lot that the syllabus recommends that we do go through as well, and we'll be working up to that. Okay, so again, like most of our work that we're doing in Extension 1, it comes down to the language a lot. So you really need to interpret what it's saying and be sure that you have a diagram that relates to that. So this one's got a diagram for us over here. So you've got a triangle and it's telling us that CA is A. So make sure you're putting that arrow on the end of the CA. Vector CB is B and D is the midpoint of AB. So that tells us that those two sections, A and D and D and B, are the same, and we need to think about that as we work it out. We want to show these two things, that vector BD, that one there, is a half of A minus B. Okay, so my first step that I always do in vectors is when I have a diagram, I want to look at the parallelogram method or the triangulation method of addition and subtraction and see what I come up with. So obviously we know we're going to need that for this question because there's an A minus B, and the only way that we're going to get an A minus B is looking at vector addition and subtraction. You may need to pause the video to make sure that you understand what's happening here with these first two rows. I basically looked at this first triangle up here and I can see that I've got that CD plus DA is going to be equal to that resultant vector CA. And I've just rejigged that and written that another way. But looking at the parallelogram method, there's our starting point there. We can see that we're going to have, what are we going to have? I'm going to have a negative CD, which is over there, and a positive CA, and that's going to equal DA. So that's by the parallelogram method, and then rearranged it to get this over here. Okay, then I've worked in that second triangle to get that second line down here. Okay, just looking at resultant vectors, what have we got? Okay, there's our starting point there. So I know that CD is my resultant vector if I use the triangulation method. So CB plus BD equals CD. Otherwise, if you use the parallelogram method, you're going to be taking away the CB from the CD to get BD. You might want to pause and make sure that you're happy with that. That's what I got for parallelogram method, and then I just rearranged it. The reason I rearranged them was that both of those two equations have CD in them. I don't have that in my first question, so I'm going to get rid of that and I'm going to make those equal. Now, this is only one way to do this question. You might find that you have another way that works for you as well. So by letting those two vector equations be equal to one another, I end up with CA minus AD is equal to vector BD plus CB. Now we have vector names for A and B, okay, so I've popped those in. And then what I've done is I've just rearranged the equation to get the A's and the B's on the one side. So I get A minus B is equal to, I might go down to this one here, BD plus AD. And that's where I'm at. Okay, and then we have a look back up at the question and have a look, okay, well, we know we've got something in the form that we want because we've got an A minus B in there and we've got a BD, and down here we've got an A minus B and a BD. So we're nearly there. But what we also know, right at the start, it said that vector A, well, it didn't say that, it said we've got a midpoint. If we have a look at the diagram, D is our midpoint. So then we know that our vector BD plus our vector DA is equal to that whole thing, BD. So if these guys are the same, I could call this vector here BD as well. So we've got two vector BDs in there equaling BA. So BD plus AD could be called two vector BDs. Halving the side, or dividing both sides by 2, I end up with my solution. So we worked our way through there, and I don't think that one was too hard. That was quite a nice one. Now, our second thing we needed to prove was that vector CD, which is that one down the middle there, is equal to a half of A plus B. Now, we could go right through that again, looking at that same kind of method and keeping our CDs. However, it's a part B, and I'm going to think, well, hence, can I use the information from before at all to help me? And in this case, I can. So from above, we had those two equations, okay? Okay, now those two equations that are numbered 1 and 2, they gave us vector CD and CD, and I'd taken them out before, okay? But I also know, I'm not going to take them out this time, but I also know from my question above, okay, I know this one, that was the part A that we've just worked out. So all I've done there is use this equation that we worked out, the one that we had from above, and I've substituted in. So if I just grab a highlighter pen to show you what I've done, where there was a BD in this equation here, I've popped in my equation that I worked out in part A. So what I've done basically is popped into that BD, I popped a half minus AB, well I've switched the sides around, but I've still got CD minus CB there. I've just swapped their sides. And then I also know that CB is vector B, so I've just popped that in there instead of CB. And what I've done is expanded that left-hand side, a half A minus a half B. And then I've added B to both sides, so that says plus B is equal to CD. Remembering that's what we want to find out. Grouping like terms, I've got a half A minus a half B plus a B is a half B equals vector C. There we go. And pulled out a half, and that's what we've wanted to prove up above. So we've gotten there. And again, you might find you get there a slightly different way. If you do and you want me to have a look at it, let me know. Let's look at the next one. Okay, it says in triangle ABC. Actually, no, I'm not going to look at this one now. I've used this one and I've looked at similar triangles. I'm going to come up with another method for this one because I think that this one's a lot easier to do without vectors. So let's jump to the next one here, which says prove that the diagonals of a parallelogram bisect each other. So we'll come back to A at another point, I think, because A is easier without vectors. So let's look at prove the diagonals of a parallelogram bisect each other. So in order to do that, you need to draw yourself a parallelogram. So I've done that. Okay, and we want to use it, show it doing vectors. Again, a lot of these proofs we can use doing geometry. I'm going to try to get these vector proofs underway because this is what the aim of the topic is basically. Okay, so this is the plan for this one. To show that AC bisects OB, so that these parts here are going to be equal to each other. What we want to do is basically show that this point where they intersect are the same points no matter what vector we're on. So we're going to let the midpoint of our vector AC, which I think I'll call C in the direction to A, be Q, and let's let the midpoint of vector OB be P. So although they look like they're crossing in our picture, they may not be, and we have to prove that they are. So it says here, to prove the diagonals bisect each other, we need to prove that P and Q are the same point. So what we basically need to do is prove that vector OP is the same as vector OQ. So from here up to P is the same as from here up to Q, therefore they're the same point, therefore it's going to be the bisector. Okay, so let's have a look what else I've written. So since P is the midpoint of OB, okay, so from O to B, P is midway, we're saying that vector OP is half of vector O to B. And the same with the other side. Since Q is the midpoint of CA, remember I've popped that from C to A, then CQ is equal to half of CA. And what we want to do now is start working in this bottom triangle here and use our parallelogram method or our triangulation method of addition and subtraction to come up with a rule for here and see if we can then substitute this in and work down to proving that OP is equal to OQ. Now let's work on that. So if we scroll down again and look at the parallelogram method of addition in that triangle, what we're going to end up with is that OQ, which I'll just move down a little bit further, is that OQ take away OC equals CQ. So that's our first part. And then I've just rearranged that to get OQ, vector OQ to subject. So that says equal to vector CQ plus vector OC. Now what we also know over here is that vector CQ is a half of vector CA. And this is where we could get a little bit stuck. Okay, so we're at OQ and we need to get to being OP. So I know that we've got a half of vector CA I've popped in for my vector CQ. But OC, what else can I do with that? Well, I actually want to try and get it all into halves. So this is kind of like a little trick. So, and that's probably not something you'd necessarily think about, but I'm going to write vector OC as a half of itself plus a half of itself. Okay. Okay. So what we can do is understand that we were told at the start that AB, OC, or they're the letters that I've named them, is a parallelogram. So we know that our opposite sides are parallel and our opposite sides are the same length. So I could write that a half of OC over here, so half of that is going to be equal to a half of AB. So I'm going to change one of those OCs to AB. So I've done that there, and now I'm going to factorize a half out of all of those terms. So it now looks like this. So at this point, you might want to go back and have a look at the diagram and see what we've got. So we've got that a half, and that's our scalar of CA plus OC is telling us it's equal to AB. So we have a look at what we can do. Can we work out a vector addition of any of these two? So if I go back and have a look at my diagram of vector CA and OC, so vector C to A and O to C, if I add those two together, that's the same as the vector O to A. I'm going to replace those first two by OA. And I've done that there. So again, you might need to pause the video or rewind and go back and have a look at what I've done there. And now I want to see what's the sum of OA plus OB. So OA plus AB is, starting here, OA plus AB is OB. So we're going to replace that with vector OB. And right at the start, we said that a half of vector OB up here is vector OP. So remembering what we've done, we've started with OQ and we've worked down to OP. So we've shown that OP is equal to OQ. So since that happens, okay, OP is equal to OQ, our vectors, then P and Q are the same point. Therefore, we have actually solved what we were after at the start, which was showing that AC and OB bisect each other. Okay, scroll down to the next page and we'll have a look at the next proof. Now, it says, given that vector OA is the column vector A0, so we know that that falls, I'm just going to go through the diagram as well, that falls onto our x-axis, okay, and we're given that vector OB is O and B, okay, so a 0x coordinate and B as our y coordinate, okay, so we've got part of our triangle. We want to prove that given that AO equals OC. Now, this was the bit when I first drew my triangle. I drew my C out here, and I'm like, well, no, that doesn't give me enough information. So what I've gone and rethought about was, well, no, what happens then if AO, which is this distance here, is equal to OC, okay, if we just pop our C down here in the negative area, then we're going to know that that point down there is going to be minus A, and we've got actually a name for our column vector, C. So C is going to be the column vector, or OC is going to be the column vector of minus A and 0. So that then actually mathematically allows us to get that O and A and O and C distance to be equal. Okay, so given that we've got now an accurate diagram that depicts that information, let's have a look at what we want to prove. It says triangle ABC is isosceles. That's what we want to prove. So we've got A, B, C, and we want to prove it's isosceles. So therefore that AB is equal to CB. Now we want to use vectors. Again, we could use other methods to prove this. Okay, we could use Pythagoras. And I guess if it didn't say to use vectors, and it was, we could use that, but we are in a vector topic, so we want to try and use vectors. And sometimes vectors are the difficult way to do that, but we're going to work it out. So here we go. So part A, let's prove that AB, okay, so from A up to B, so that's my direction of my vector, is equal to CB. So I've gone from C to B, well, that would be the same as BC. So it doesn't really matter which way you go, whether you go AB, BC, or CB, you're going to end up with a negative, and it's one way or the other, and it will still work through. So the way that you do it might be slightly different to mine. Okay, what do we know? Okay, so I've said that OC, okay, that vector there is equal to OB plus BC. And that's why I chose to go BC instead of CB. We also know that BC is equal to OC minus OB. Okay, so I've just rearranged those two formulas to get to the second one. We also know that OB, okay, this vector up the middle here, is equal to O to A plus A to B. Okay, that's my directions of my arrows that I've chosen. Okay, if you chose different directions, then you'll have a different subtraction or addition, and that's okay. That would flow through as well. So I've just rearranged that to get that AB is equal to OB subtracted from vector OA. So we've got these two things here. Okay. Now, we were given that AO and OC are the same. Okay, that this vector here is the same distance as that vector there. So we know that. So O is the midpoint. And we can then write vector OC as minus AO, which I wrote before. And we've already got what vector OB and OA was, so we can actually work out what vector AB is. So vector AB is going to be OB, which is 0B, minus OA, which is AO. Take away the x's, take away the y's, we get minus A and B. Okay, now we also know from this part here that vector BC is vector OC minus OB. So I've just written that one in vector form. So BC is equal to OC, which is minus A0, minus our vector OB, which is OB. So we get that vector BC is minus A minus B. Okay, now let's remind ourselves what we wanted to prove. We want to prove that AB equals CB. Now, that's not a vector, that's a distance. So we want to find the magnitude of AB and show that that is equal to the magnitude of CB or BC, depending on which direction that you went. This is where it's not going to make much difference which direction your vector went, because when we square things, we square the negatives and the negatives go away. So let's have a look down here. So the magnitude of vector BC, remember looking at our magnitude formula, which we've worked on, and it's on the HSC formula sheet, is the square root of the x components plus the square of the x components plus the square of the y components, and we square root them. So when we pop that through for BC, okay, there it is. We've got minus A all squared becomes A squared minus B all squared becomes B squared. So that's our distance, BC. Doing the same for our vector AB, which we've got here as the point minus, as the vector minus AB, squaring our A's components, squaring our B's here, we've got A squared plus B squared in the square root, which is the same. Okay, these guys are the same. So I've written that as the magnitude of vector BC is equal to the magnitude of vector AB, therefore BC equals AB, therefore the triangle is isosceles. So that's my way of working it out. Again, we could actually work that out using similar triangles, Pythagoras' theorem, and equating distances along here. So we could definitely do that, but we're given vectors, so we need to prove that in terms of a vector. Now, if we were going to have a look at what the angles were in part B, that angle ACB, which is that angle I popped in for theta down there, is equal to angle CAB, which is alpha in there. I'm going to work that out. I'm going to let you do that, but there's various ways that you could do that. Okay, we know that there's right angles in here. Okay, so we could work out that the magnitude of all these sides are, so the magnitude would be B and A, therefore tan of theta would be B on A, tan of alpha would be B on A, the angles would be the same. Or you might decide to use the cosine rule and working in a triangle that has a side there and there being the same as that side there and there. So you've got options to work that one out. Okay, so you want to have a play around with that one. Now, what I suggest you do after you finish these proofs, because we're finished in there for today, is I want you to go back into the OneNote, and if you go and scroll down the side, there's some really great work here under the skills sheets on geometrical proofs using vectors. And what this does is it really works you through these bit by bit. So stepping you through, looking at how you would work through each of those, and I've tried to line up the answers as much as I can over to the right hand side, and you can step through question and answer and have a look through those. I particularly like 2. You can have a go at 2. That would be great to have a look at. That one's in our syllabus, suggesting that we have a look at that one. I want you to have a look at that first. Otherwise we'll have a look at it next lesson, but I've also got that one there popped down in topic guidance for vectors. That's popped out of the syllabus there. We'll have a look at this in class at a later date, but if you want to look at that, I've done a proof similar to that in there. over to the right. And this is what the syllabus is saying we really need to do. So there's some interesting things in here that I've worked through, and there's some stuff over to the right over there that you might want to work through as well if you're feeling really confident. But I suggest going back, working through the geometrical proofs, okay, and then having a look at 1004, which is in our textbook in the Maths in Focus, and working through that with the answers as well.